Have you ever wondered what the night sky looked like before a single star was born? Imagine a cosmos without starlight, no galaxies, no suns, no planets, just a vast, expanding darkness filled with invisible potential. This was the universe mere hundreds of thousands of years after the Big Bang, a silent, seething sea of primordial particles waiting for the first spark of nuclear fire. To understand how the first stars known as population 3 stars were born, we must journey back to the infancy of time. About 13.8 billion years ago, the universe emerged from a hot, dense singularity in the event we call the Big Bang. In the first few minutes, the universe expanded and cooled just enough for the first atomic nuclei to form in a process known as Big Bang nucleosynthesis. But these nuclei were simple, mostly hydrogen and helium, with tiny traces of lithium and beryllium. Heavier elements didn't exist yet. The universe was chemically primitive. For hundreds of thousands of years after that, the universe was an opaque fog of charged particles and photons, scattering light and making the cosmos effectively invisible. This was the era of the cosmic plasma. But eventually, around 380,000 years after the Big Bang, temperatures dropped low enough for electrons to combine with protons, forming neutral hydrogen atoms. This moment, known as recombination, allowed light to finally travel freely across space, marking the birth of the cosmic microwave. Background CMB. Now the universe was transparent, but still dark. There were no stars, no light sources, only cool gas slowly pooling under the influence of gravity. This period, called the Cosmic Dark Ages, lasted for hundreds of millions of years. But gravity never sleeps. Tiny fluctuations in the density of matter, seated during inflation, began to pull gas together into clumps. Over time, these clumps grew larger, becoming the first dark matter halos, the scaffolding on which galaxies and stars would eventually form. And here, in these invisible wells of dark matter, where hydrogen and helium collected and collapsed under their own gravity, the first stars were about to be born. But these were no ordinary stars. Without metals to cool the gas efficiently, the clouds had to collapse into massive clumps. Simulations suggest that the very first stars were giant stars, 200s of times the mass of our sun, hot, short-lived, and extremely luminous. They would change the universe forever. But what exactly triggered their formation? What were the physics, the conditions, and the processes that made the leap from darkness to light possible? That's what we'll uncover next, as we explore the mysterious birth of population 3 stars, the first cosmic lighthouses in a universe of shadows. They were the first lights in a dark universe, the cosmic pioneers. But what exactly were these population 3 stars? And how were they different from every star that came after? To answer that, we need to understand one of the most fundamental concepts in stellar astrophysics: metallicity. In astronomy, metals refer to all elements heavier than helium. This includes carbon, oxygen, iron, and even the calcium in your bones. Modern stars, like our sun, are considered population-ized stars rich in metals that previous generations of stars have produced. Stars like those in ancient globular clusters are called population 2, older and poorer in metals. But population 3 stars, they had no metals at all, formed from the pristine gas of the Big Bang. These stars were made almost entirely of hydrogen and helium, the only elements that existed at the time. And this lack of metals had profound consequences. Metals play a crucial role in cooling star-forming clouds. In modern stellar nurseries, dust and heavy elements help the gas lose heat, collapse more efficiently, and fragment into many small stars. But in the early universe, with no metals to aid cooling, gas clouds could only cool via much slower processes, such as molecular hydrogen emission. This meant the collapsing clouds were hotter, larger, and more massive, leading to the formation of very massive stars, far bigger than the stars we see today. Theoretical models and simulations suggest that population 3 stars ranged from tens to hundreds of solar masses, with some possibly reaching up to 300 times the mass of the sun. These stars burned extremely hot, lived very short lives, only a few million years, and ended in violent explosions. Some may have gone supernova, enriching the surrounding gas with the first heavy elements. Others, even more massive, may have collapsed directly into black holes, possibly seeding the formation of supermassive black holes at the centers of galaxies. Because they were so massive and hot, population 3 stars emitted huge amounts of ultraviolet radiation, capable of ionizing the hydrogen around them. This initiated a cosmic transformation known as the epoch of reionization, which lit up the universe and made it transparent once again. But despite their theoretical importance, no population 3 star has ever been directly observed. They lived fast, died young, and left little behind that we can see. So how do we know they ever existed? That's where astronomy becomes detective work. By studying the chemical fingerprints of ancient stars and galaxies, and simulating the early universe with powerful supercomputers, scientists have pieced together a compelling case for their existence. Still, one question haunts astronomers to this day. Could we ever find one? The answer may lie in the next part of our journey, where theory meets technology, and telescopes like the James Webb Space Telescope scan the farthest reaches of space, searching for the afterglow of the first stars. What if the very first stars in the universe have all vanished, leaving behind no visible corpses, no shimmering remnants, only fingerprints written in the chemistry of other stars? That's exactly the mystery astronomers are trying to solve. Despite decades of searching, no population 3 star has ever been directly observed. These ancient giants, forged from the pure hydrogen and helium left by the Big Bang, lived fast and died young, burning out in just a few million years. Given the universe is now over 13.8 billion years old, any surviving Pop 3 stars would be an extraordinary rarity, if not impossible. But scientists haven't given up. Instead of looking for direct light from these long-dead giants, they're turning to forensic astronomy, examining clues left in the next generations of stars, galaxies, and explosions. Let us look at 3 major types of evidence that point toward the once glorious presence of population 3 stars. 1. Ancient metal-poor stars in the Milky Way. While Pop 3 stars themselves are long gone, some of their descendants may still be alive. In the halo of our own Milky Way, astronomers have discovered extremely old stars with ultra-low metallicity, meaning they contain almost no elements heavier than helium. One such example is the star SMSS J0313O, 36 to 670,839, found in 2014. It contains iron at a level 10 million times lower than the Sun, and yet shows strange abundances of lighter elements like carbon and magnesium. This pattern suggests it was formed from the ashes of a population 3 supernova. The explosion of the first star didn't completely enrich the gas cloud, but instead left behind a signature of selective elemental distribution. These stellar fossils act like cosmic DNA evidence, clues pointing to an ancient ancestor we've never seen. To unusual supernovae in the early universe. Another key clue comes from the types of supernovae observed in distant galaxies. Certain extremely bright and energetic explosions called parent stability supernovae can only occur in stars with masses between 140 and 260 times the mass of the Sun, and these are precisely the masses predicted for population 3 stars. These explosions don't leave behind black holes or neutron stars. They completely disintegrate the star, enriching the surrounding space with specific elemental patterns. While we haven't conclusively identified a parent stability supernova in action, the elemental fingerprints of such events have been detected in deep spectroscopic surveys, hinting at their presence. Billions of years ago. 3. The role of JWST. Looking deeper than ever before. Finally, the James Webb Space Telescope JWST has opened an entirely new chapter in this quest. Unlike Hubble or Spitzer, JWST is designed to observe the universe in infrared light, perfect for detecting extremely faint, redshifted galaxies from the early cosmos. Already, JWST has identified galaxies forming just 300 to 400 million years after the Big Bang, an era in which population 3 stars should have dominated. By analyzing the spectral signatures of these ancient galaxies, astronomers are looking for missing metal lines or unusual ultraviolet emissions that could hint at the influence of POP3 stars. In 2022, one such candidate was found, a galaxy with an exceptionally hard UV radiation field and low metallicity, possibly indicating the presence of population 3 stars within it. While not conclusive, these are the strongest hints yet. In the end, while we may never observe a population 3 star with our own eyes, their ghosts echo in the light of younger stars, the chemistry of ancient survivors, and the deep signals from the edge of time. In next part, we'll explore how the James Webb Space Telescope is specifically engineered to track these ancient beacons, and whether we might finally catch a glimpse of the first light. Despite their theoretical importance, population 3 stars have never been directly observed, and for good reason. These stars were formed over 13 billion years ago, and due to their enormous mass, they burn through their nuclear fuel incredibly fast, exploding as supernovae in just a few million years. That means none of them have survived to the present day. Astronomers are thus left with an enormous challenge. How do you study something that no longer exists? The key lies in indirect detection, searching for cosmic fingerprints left behind by these early stars. One method involves analyzing the chemical composition of ancient gas clouds and stars that formed shortly after the first supernovae exploded. If these objects lack heavier elements like iron or carbon, but show trace amounts of lighter elements like helium and lithium, they may preserve the chemical imprint of population 3 stars. Another strategy is to detect the supernova explosions themselves. These early stars likely ended their lives in powerful parent stability supernovae, a type of explosion that only occurs in stars with masses between about 140 and 260 solar masses. These events leave behind no black hole or neutron star, only vast amounts of light and debris. If we can spot one of these distant, energetic bursts, it could serve as a cosmic fossil from the age of the first stars. There is also the 21-centimeter hydrogen line, a specific radio signal emitted by neutral hydrogen atoms in the early universe. Tiny fluctuations in this signal can reveal patterns of heating and ionization caused by the intense radiation of population 3 stars. Projects like the Hydrogen Epoch of Reionization or AHERA are attempting to map these faint signals to reconstruct the timeline of early star formation. But the most exciting tool in the astronomer's toolkit today is the James Webb Space Telescope, JWST. The James Webb Space Telescope, JWST, was designed to peer deeper into the universe and further back in time than any telescope before it. With its infrared capabilities, JWST is uniquely suited to study the early universe, where light from ancient stars has been stretched and reddened by the expansion of space. But can it actually find population 3 stars? While individual population 3 stars are likely to faint and short-lived to be resolved directly, JWST is helping astronomers spot candidate galaxies formed in the first 200 to 400 million years after the Big Bang. These galaxies might host the last generation of population 3 stars or contain the chemical remnants of their violent deaths. One of JWST's early breakthroughs was the detection of galaxies at redshifts greater than 1.0, meaning their light has taken over 13.3 billion years to reach us. These galaxies are incredibly compact and luminous, and some show unusual spectral signatures that hint at low or zero metallicity, a key feature of population 3 stars. In particular, astronomers are searching for the presence of strong helium emission lines without accompanying metal lines, which would signal the presence of very hot, massive, metal-free stars, a hallmark of population 3 populations. A few galaxies observed by JWST have shown unusual ultraviolet and Lyman alpha emission profiles that match theoretical models of such stars. One promising candidate, identified as CE or S93316, lies at a redshift of Z-16.7, making it one of the earliest known galaxies. Its extreme brightness and spectral energy distribution suggest a population of massive, short-lived stars, possibly including population 3 remnants or immediate successors. While JWST hasn't yet confirmed the direct detection of a population 3 star, the data it's collecting is narrowing the gap between theory and observation. And as new software and analysis techniques evolve, it's only a matter of time before we find definitive clues to these long-lost stars. But the question remains, why does this matter? Why should we care about stars that lived billions of years ago and have long since died? The answer lies in their legacy. Although population 3 stars vanished billions of years ago, their impact echoes through every corner of the universe today, including within us. These first stars acted as the catalysts of cosmic evolution by fusing hydrogen and helium into heavier elements and then exploding as supernovae. They injected the first metals into the surrounding medium. Without this enrichment, no planets, no rocky worlds, no carbon-based life could have ever emerged. You and I, the Earth, the air we breathe, the calcium in our bones, the iron in our blood, all are made from elements forged in the hearts of stars. But it all began with the death of the first ones. Population 3 stars also helped reionize the universe after the cosmic dark ages. Their intense ultraviolet radiation began breaking apart neutral hydrogen atoms, making the universe transparent to light. This process of cosmic reionization was essential for the development of galaxies, stars, and ultimately, observers like us. Even the structure of the universe, the way galaxies cluster, the evolution of dark matter halos, the distribution of gas was influenced by the formation and feedback from these early stars. They played a key role in shaping the initial conditions for galaxy formation. In short, without population 3 stars, there would be no complex chemistry. There would be no Earth-like planets. There would be no life as we know it today. Astronomers search for the faintest traces of their fingerprints, unusual chemical abundances in ancient stars, gravitational wave signals from early black hole mergers, and galaxies with strange spectral lines. These investigations are not just academic. They are about uncovering our deepest roots. As new tools like JWST, 30-meter class ground telescopes, and next-generation gravitational wave observatories come online, we may finally get our first direct evidence of these mythic stars. And perhaps most poetically, as Carl Sagan once said, we are made of star stuff. That stuff, those atoms that make you and me, began their journey in the fiery hearts of the universe as first cosmic beacons, the population 3 stars.